If you've ever integrated a radio module into your own board and you thought, everything is 50 ohms, this should be fine, then this episode might hit a little close to home. You validate the module on the evaluation kit. Range, good. Sensitivity, also good. And then you design your own board. You add a connector and a cable so you can mount the antenna where it actually fits in the enclosure. And now suddenly you're down a couple decibels and the range is a little worse than you expected. There's no smoke. There's no dramatic failure. There's no big explosion. It's just a nagging gap between what the datasheet promised and what your prototype actually delivers. And what's really frustrating here is that the radio is the same, the antenna is the same, and the frequency is the same. And that's often where these teams start second-guessing the antenna or the matching network. But very often, the issue isn't there. It's in the transition. It's that point where your controlled impedance PCB trace becomes a connector, and that connector becomes a cable. Today, we're going to talk about coax from the perspective design engineers care most about, and that's the common problems, the hidden risks, and the practical ways to reduce them. This is not a connector catalog episode. It's an episode about RF risk. You're listening to Würth Elektronik's What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and today, coax connectors. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. Let's start with that one concept that makes the rest of this episode actually make sense. 50 ohms. That is the value that gets thrown around a lot when we're talking about RF systems. But in this case, it's not a resistor value. It's a characteristic impedance, a wave property set by geometry, really. Now, this is a bit more advanced podcast episode, but in case you forgot, RF stands for radio frequency, which refers to electromagnetic waves used to transmit information wirelessly. Now, if you're an experienced designer and you still forgot, don't worry, your secret is safe with me. A coaxial cable is built so that the ratio of inductance per length and the capacitance per length produces a consistent impedance. Now, your PCB trace, if it is designed correctly, it does the same thing. So when we say that a cable is 50 ohms, we are not saying that it measures 50 ohms on a multimeter, because it won't. It'll look like a short or an open depending on how you probe it. We're saying that a traveling RF wave sees a predictable relationship between the voltage and the current as it moves down that structure. Now, this matters because when that wave encounters a sudden geometry change, the impedance changes. And when impedance changes, some energy reflects. Reflection is physics enforcing boundary conditions. And in real products, you don't need a catastrophic mismatch to lose performance. If you lose 1 decibel, you've lost close to 20% of your power. RF systems rarely fail catastrophically. They lose margin incrementally, and that 1 decibel might not come from a single huge mistake. It could come from multiple small discontinuities and losses that are stacking together. So now let's talk about where those hidden losses tend to live. A lot of teams treat the connector as a mechanical boundary, but it's not. Now, electrically, the connector is a continuation of the transmission line, and the transmission between a PCB trace and a coax connector is one of the most common places where impedance discontinuities appear. Now, even if you did everything right on the PCB trace, adding a connector can introduce a mismatch. So why is this? Well, it's because the connector center contact introduces a geometry that's not identical to your PCB trace. It has its own diameter, its own spacing to ground, and its own dielectric environment. So, what are the real-world failure modes? First, the center contact style and the landing geometry on the board can generate a localized impedance bump. A round post-style center pin has more metal volume and can create a larger discontinuity if the trace transition isn't tuned. A flat tab style often creates a smoother transition and can be easier to match because the geometry is less abrupt. Second, the solder joint itself can create unexpected geometry. In some connector styles, gaps between the connector body and the PCB can leave an air region where you thought you had consistent dielectric. That changes effective permittivity and local impedance. A tiny gap can matter more than you want it to at several gigahertz. Now, third, the ground return path can be a real problem. A coax transition is not only the center pin, it's the return path in the outer conductor. So if your connector footprint does not provide a low impedance, symmetrical ground connection to the PCB reference plane, you can create current crowding and parasitic inductance right where you want it least. Connector selection and footprint design should be treated as signal integrity decisions and not mechanical afterthoughts. This is why those end-launch connector styles exist. The goal is to provide a direct transition to PCB transmission line structures with minimal discontinuity and better impedance continuity. If you're building your first RF system with coax, this is quite often the first place that you learn that RF is not about connecting pins, it's about shaping geometry. So here's one practical rule that pretty much sums up this whole section. If your RF trace reaches a connector and the layout around it looks like normal digital, that is a warning sign. RF transition regions should look intentional. Now let's move downstream through the connector and into the cable. Cable choice is one of the easiest ways to lose link budget without realizing it. Engineers, quite oftentimes, they pick a cable that's based on geometry, flexibility, and what's convenient in the enclosure. Those are legitimate constraints, but cable choice also controls attenuation, and attenuation is rarely intuitive. Loss increases with frequency. That's not optional. It's driven by conductor loss and dielectric loss. At higher frequency, skin effect concentrates current near the conductor surface, increasing effective resistance and the heating. So two cables that feel equivalent mechanically could behave very differently electrically. Also, cable frequency support categories matter. So if your system operates in the multi-gigahertz range, picking a cable family that was really designed for these lower frequency use is a classic way to erode margin. You might still pass a functional test and you might still connect and transfer data, but you'll have less range, less robustness, and less tolerance to production variation. So now you add one more factor, and that's mechanical routing. Every coax cable has a minimum bend radius, and when you exceed that, you deform the dielectric and braid structure. That changes geometry, which changes impedances, which therefore creates discontinuities and additional loss. And the painful part is that bend radius violations often don't show up as immediate failure. They're going to show up as, why is performance worse on some units? Or why does it drift after thermal cycling? Or even, why is it sensitive to how the cable is routed? So cable selection is a balancing act between frequency range and attenuation, flexibility and bend radius, temperature range and environment, shielding effectiveness and interference susceptibility, and also cost and manufacturability. So the key message is this: if you're tight on margin, cable is not the secondary decision, it's going to be your primary one. Our next risk is vibration and mechanical stress. RF performance is sensitive to both of these. Now, many connector families exist not because engineers love having 10 connector types, but because applications demand different coupling mechanisms, retention forces, environmental sealing, and mating cycle capabilities. A bayonet coupling might be great for quick connect in a lab environment, but a threaded coupling is best when vibration resistance and retention matter. In some connector families, Retention systems vary by design. For example, in push-on connector families used in dense, space-constrained environments, detent systems can be selected based on retention force and mating cycle requirements. Now, this matters because micro-movement and contact stability affect the electrical interface over time. So if your product lives in a harsh environment, or it sees vibration, or gets mated and unmated repeatedly, then connector family choice is not only about size and convenience, it's about stability of performance. 2 units can measure the same on day 1 and diverge over months, and this is due to mechanical realities that you could actually predict up front. Now, the mitigation is not complicated, but it, again, has to be intentional. So choose connector families aligned with a mechanical environment. Consider retention, mating cycle expectations, and sealing needs, and treat field handling as a design input and not a documentation footnote. So now we get to the big one that design engineers and manufacturing engineers both feel, and this is prototype success does not guarantee production repeatability. In early builds, it's really common to see cables terminated manually or assembled with inconsistent strip lengths, crimp compression, solder wetting, shield termination, and strain relief. At low frequency, the impact may be negligible. At higher frequency, those geometric differences can become measurable. This is one of the reasons that teams sometimes chase RF ghosts in late-stage validation. It's not supernatural, it's variability. So one mitigation strategy is to reduce inconsistencies in lab-built cables. This is where custom cable assemblies can make a real difference because they provide controlled termination methods, cable type selection for frequency and attenuation goals, repeatability length and routing assumptions, consistent shield termination and strain relief, and reduced assembly time and reduced chance of handling damage. There are many custom cable options that are available in surprisingly reasonable quantities. Now, for some teams, the real win here is not that the cable exists. The win is that the cable performance becomes predictable and the integration risk becomes smaller. So to wrap it all up, RF systems rarely fail dramatically. They're going to fail incrementally, a fraction of a decibel at a time, a small impedance discontinuity at the PCB-to-Connector transition, or maybe a cable attenuation that eats margin at frequency. It could be a bend radius violation that creates a local impedance change, mechanical stress that degrades stability over time, or even production variation that turns a good prototype into inconsistent units. When you treat coax as a mechanical detail, these risks show up late. But when you treat coax as part of the transmission line system, you can design around them early on. And early is where design engineers still have options. That's the goal, not just picking up a connector, but protecting system margin. And if you're ready to get hands-on with your design, whether it's RF, or passive components, connectors, anything in between, we encourage you to visit Würth Elektronik online at www.we-online.com. That's www.we-online.com. You're listening to Würth Elektronik's What's Up Radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.